Okay. So, we have just defined the semantics of first order logic, and now we want to move on to proof systems in FOL, because eventually that is what we are interested in, writing programs which can produce true statements. So, the first thing to observe is that all the rules that we have studied so far, things like modus ponens, they still hold in FOL as well. So, we carry forward everything that we have in propositional logic to first order logic, but what is different in first order logic is that we have quantifiers and we have predicates, and we want to talk about how to handle those essentially. Now, the first thing to observe is that these quantifiers are essentially short forms essentially. So, when I say something like, okay, let me first state this. So, if I were to make a statement like for all x p x, where p is some formula or predicate, then I am essentially making a statement which is logically equivalent to saying that P A, where A is some constant in my domain or some element of my domain, and P B, where B is another element of my domain, and P C and so on for every element. Which is true of formula, all formulas in general. It could be, it does not have to be arity 1, it could be P x y and things like that essentially. So, the first thing to observe is that the universal quantifier is essentially a short form for making a statement which is true about every element of the domain essentially. So, I could have written the larger conjunct, especially if my domain is finite. So, let us say if I am talking about this particular class which has 20 odd students, I could have written some statement for each student, and that would be equivalent to saying for all x, something like that. Likewise, there exists x p x, or let me use a predicate with two variables. So, let us say there exists y, there exists x, is equivalent to saying that P A or P A B or P A C or P B B and so on. It is just a large disjunct essentially. So, which of course explains the semantics of these quantified sentences quite easily, is that a sentence like for all x p x will be only true when it is true for every element in the domain, whereas a sentence like there exists an x p x. So, for example, there exists a number which is E 1 will be true as long as for some element it is true essentially. So, this will give us some insight into the two rules of inference that we need to add to FOL essentially. So, essentially there are two rules we need. One is, and I will illustrate them using predicates of arity 1, but they carry forward to predicates with more arguments as well. So, first rule says is that if you have a formula of the kind for all x p x, then you can infer P of A, where A is some constant in the domain essentially. Now, you can see that if you look at the fact that for all x p x is just an abbreviation for a large conjunct, this is just an instance of simplification in some sense essentially, because we in propositional logic we said that if P is true and Q is true, then you can infer that P is true essentially. This rule is called universal instantiation. We use the term UI in short essentially, and it is one of the most common rules that we use in first order logic. Essentially it says that for x you can substitute anything, you can even substitute a term which is, let us say some function of x or something like that, it does not matter, some function of a constant. Anything you put in, any term that you give as an argument to this predicate, this formula must be true. So, you can substitute anything. The other rule is the opposite, which says that if you are given that a predicate is true for a certain element A, then you know that this formula is true, and this formula says there exists x p of x. Because this formula is only saying that there exists at least one element for which this formula must be true, and we already know that it is true for A. So, there exists an x p x must be true. This rule is called generalization. Then just as we had rules of substitution in propositional logic, we also have rules of substitution in FOL. Which means you can substitute one formula for another formula, and you might be familiar with these kind of formulas. So, the two most common rules that we will use are the fact that if you have a negation of a universally quantified formula, then that is logically equivalent to a formula which is an existentially quantified formula with the negation inside. In other words, you can move the knot inside, and when you move it inside, it changes the nature of the quantifier essentially. As you would expect, this is called De Morgan's law. And it is easy to understand if you remember the fact that a universally quantified formula is basically a large conjunct essentially. And we already know from propositional logic that when you take a formula which is a conjunct and take the negation of that, and when you push the negation inside, then it becomes a disjunct essentially. So, that is what is happening here essentially. Or if let us say P stood for mortal essentially. Okay. So, P x says that x is mortal. This sentence is saying that it is not the case that everything is mortal essentially, which of course is logically equivalent to saying that there exists at least one element which is not mortal essentially. So, to say that it is not the case that everything is mortal is equivalent to saying that there exists something which is not mortal essentially. And likewise, if you move the sign across a existential quantifier, we get a universal quantifier. So, if you were to say if now let us say P were to stand for immortal, then you are saying on the left hand side that there is no one who is immortal essentially. There does not exist anyone who is immortal. It is equivalent to saying that everyone is not mortal essentially. Right. everyone is not immortal essentially. And then you have the usual rules which are like commutativity and so on. So, if you have a formula for all x for all y p x y, you can write equivalently for all y for all x p x y. It does not matter as long as the quantifier is of the same nature essentially. If it is a universal quantifier, you can change the order in this thing. Why do we need these rules? Because we are talking about now formal systems. We are talking about formally manipulating formulas to either produce a formula we are interested in or produce a proof of some kind essentially. Then I will encourage you to look at. So, if you look at this formula for example. So, this same thing holds for existential quantifier. But if I were to look at a formula like this for all x, there exists a y p x y, and if I were to try to say that there exists a y for all x p x y, which means I try to interchange the two quantifiers, then this formula is false actually. It is not true. So, you cannot use it as a rule of substitution, that if you have this if you have the left hand side for example, you cannot replace it with the right hand side. In this particular example, it so happens that if you have the right hand side, you can still replace it with the left hand side, but that means that you can write a rule of inference which says there exists y for all x p x y implies for all x exists y p x y. If you look at the left hand side, let us say P stands for admires. Okay. So, P x y stands for the fact that x admires y essentially. So, the left hand side is saying that there exists some y who everyone admires. There exists a y such that for all x P x y is true. So, let us say Sachin, a non controversial example. You can say that everyone admires Sachin, which is true essentially. The right hand side is saying that everyone admires someone essentially. For all x, there exists a y such that P x y is true. Now, because we know that everyone admires Sachin, this right hand side is true, because for every person there is at least one person whom you admire essentially, which is Sachin. So, certain things hold in one direction essentially. So, I will encourage you to look at quantified formulas where you have two quantifiers, or maybe you have just one quantifier, and you look at formulas like this. There exists an x. So, this is an exercise P x and Q x is equivalent to there exists an x P x and Q x. So, I am leaving as an exercise. Okay. So, look at both the quantifiers, the universal quantifier and the existential quantifier. Look at this common conjuncts, which is and or, and try to see which sets of formulas are equivalent essentially. So, let me give you an example. So, if I say for example, P stands for the fact that a number is even and Q stands for a number is odd essentially. Then if I have a formula which says there exists a number which is even or odd, and I say the other side is there exists a number which is even or there exists a number which is odd, then you can see that both the sides are true and both the sides are can be replaced with each other essentially. So, I wanted to sort of study these formulas and look at all combinations of and or and the two quantifiers essentially what we can do.
So, aren't there any rules of precedence?
No.
Of precedence? Like which one
No.
goes from left to right, right to left?
We have not talked about precedence at all in this logic, because we use brackets everywhere essentially. Wherever brackets, wherever it is clear that brackets can be thrown away, we will throw them away essentially. So, we never say things like multiplication has a precedence over addition. That is only if you do not use brackets. If you use brackets, you do not need precedence essentially, I think, right.
Okay, for example, here for all x there exists y. In that case, there is no precedence.
There is no question of precedence. The scope of a quantifier is whatever follows the quantifier. I could have actually put brackets essentially. So, this statement for all exists there exists a y. If I were to really put brackets, then I would first have to put a bracket out which says that this is the scope of for all x, and then I would say that whatever follows this is the scope of the existential quantifier. That is implicit essentially, I think. If you remember, when we define the syntax, we had put brackets, but in practice we do not really put brackets unless there is a need to do so. Okay, so, these are the kind of rules of inference that we need. So, let us try talking about proofs now, and let us take our favorite rule of inference, which is modus ponens essentially, and let us work with our favorite example. Since we have started the course, we have not been able to prove that Socrates is mortal, I think. So, today let us try and do that. What are we given? We are given the example that all men are mortal. Then we are given that Socrates is a man, and we want to be able to prove that Socrates is mortal. So, from the semantics of the language, we know that this is indeed entailed. So, let us write this in first order logic. So, for all x, man x implies mortal x. And let me leave a little bit of a gap, because I need to make a couple of inferences. Then we are given Socrates is a man, which we express as this man Socrates, and we want to infer that mortal Socrates. We were not able to do this in propositional logic, because if you put each of these three sentences as propositional variables, there is no connection that you can see between them essentially. But now we have richer language, and we have more rules of inference that we can exploit essentially. So, what do? We first apply the new rule that we have just learned, which is the rule of universal instantiation. This rule says that in any formula which has a quantified variable, universally quantified variable x, I can replace x with anything I want essentially from the domain essentially. In particular, I can replace x with Socrates. So, I get a new formula, a new sentence, which says that man Socrates implies mortal Socrates. Now, you can see things are simple. I have a statement. So, if I put man Socrates as P, and mortal Socrates as q, then I have p implies q, then I have p below that. So, I can infer q, which is the rule of modus ponens that we inherited from propositional logic essentially. So, we can just simply apply that using modus ponens, and we have the proof for mortal Socrates. We have generated the formula that Socrates is mortal, and that is the notion of a proof. Right. So, this form of reasoning, as you remember, is called natural deduction. So, we will start with natural deduction, and we will show that natural deduction is not, or direct proofs as we call them, are not complete. They were not complete in the case of propositional logic, and they are not complete in the case of first order logic essentially. But we will start with that, because that is a very useful system to have, and we will also call this as forward reasoning. And in particular, we will use a term called forward chaining, which is a natural form of forward reasoning, and I will shortly describe what we mean by this. Now, one problem here is that there is a guess involved. Of course, we can make informed guesses as to what to substitute for a variable, but nevertheless remember that we are trying to write programs to do this essentially. And if there is a whole set of statements we are working with and a whole set of guesses we have to make, then it may not be such a simple task. So, there is a problem with forward reasoning, that we have to make a guess essentially. The other slightly smaller problem is that you have to remember, we are talking about writing programs, that you have to process the quantifiers and handle them and parse them and do things like that, which can be more work in terms of processing essentially. So, what we will do is that we will look at a variation of this rule, which is used in forward chaining, and which is to use implicit quantifier form which will also address this problem of guessing essentially. Because it is clear when we look at the target that we want. What is the target? The target is this instance of the universally quantified statement where x is substituted with Socrates, and it is clear by looking at what we want to prove that we are talking about Socrates. So, we want to basically associate the fact that Socrates is a man with Socrates being mortal essentially. So, in this implicit quantifier form, we do not write the quantifiers. So, today we will only look at the universal quantifier, because a lot of knowledge that we want to store is going to be universally quantified, things like all men are mortal, all students are bright, all leaves are green, and all kinds of relations between things which are universally quantified essentially. And we will first focus on that. We will look at existentially quantified variables a little bit later. So, what we will do is that we will take a universally quantified variable let us call it x and replace it with a distinct form where we will, which will make us kind of remember that it is universally quantified. So, what we will do is that we will just put a question mark below the variable and keep in mind when we are writing our programs that the question mark stands for the fact that x is universally quantified essentially. So, instead of saying that for all x man x implies mortal x, we will now write this as man x implies mortal x. This is just a change of notation essentially. Okay. It does not change the sentence. The sentence is still the same. It is just that we are not writing the quantifier and we are remembering that fact by putting a question mark below the variable essentially. So, every time you see a variable with a question mark, you must remember that it is a universally quantified this thing essentially. So, I can still apply universal instantiation to this for example, and produce a formula which is true for Socrates essentially, but we will not do that. What we will do is that we will try to now apply it directly. We will ask the question as to what is it that will make these two formulas the same. I will just use the term expressions, and when we say we mean identical, and the answer to this is a substitution x with Socrates. So, I will use not x. So, substitute the string not x with the string Socrates, and so again you must keep in mind that this is a constant in my language. So, I can substitute it with a constant. In fact, I can substitute it with any term essentially. In this case it happens to be a constant and this is a variable. So, I can substitute a variable with a constant or any term essentially. So, let me actually write term here. So, we call this thing a substitution, and a substitution often denoted by Greek letters, for example, theta says that I have a set of pairs which are variable and term. So, a substitution is a collection of variable term pairs or a variable value pairs as some books would say, and in particular the substitution that we are interested in is, in our example, theta says that the variable that we are talking about is x. Maybe we will sometimes put the question mark here, sometimes not, because it is really clear from the context as to what we are talking about, but we are substituting x with Socrates, and this is what our theta is essentially in this example essentially. Now, if we apply the substitution, So, we have this notion of applying a substitution to a formula. It means basically substitute whatever is other variables that are talked about in the substitution with the values that are given in the substitution. So, remember substitution is a list of variable value pairs, and we apply this to get a new formula essentially. So, once we do that, then we can directly infer mortal Socrates. So, this rule which allows us to do this, it takes these two formulas and infer this formula by applying a substitution. So, theta that we are applying is this one here, is we will call this as modified modus ponens. Or MPP. So, a modified modus ponens can be applied to a formula in an implicit quantifier form, and what it needs is that you must be able to make the left hand sides of the implication and the other statement somehow identical by applying a substitution, and then you can apply the same substitution to the right hand side of the implication to infer that essentially. So, I will stop here. We will formalize this notion in the next class, and we will also look at the algorithm which is needed for making these expressions identical, and this algorithm is called the unification algorithm, which we will study in the next class. Okay, we will stop here.